Today we will discuss the what is the relation between the natural coordinates and its global coordinates. At the same time, how to find out its derive the shape functions by using its natural coordinate system. We'll learn. So, in this, first we consider the two-noded element with global coordinates. This one is global coordinate system. It is located in x1 distance from the origin and x2 distance, node 2 and node 1. So this is the global coordinate system. Now what is not natural coordinate system? The magnitude of its axis varies from -1 to 1. That is called the natural coordinate system. In this natural coordinate system, we consider the two-noded bar element with node 1. Magnitude is -1, node 2 is +1. So it varies from -1 to 1. That is the natural coordinate system. So we need to derive what is the relation between these two. So zeta is equal to 2 by x2 minus x1 into x minus x1 minus 1. This equation 1 shows the relationship between this natural global coordinate system. So we will find out whether it is satisfying its boundary conditions or not. First we will check it with. So in this equation 1, suppose we may choose this one is x is at x1. What will happen? Suppose we substitute in the place of x1 minus x1 is 0. The total term will appear as 0. So -1 is left. Means at here x1 is x is equal to x1, the zeta is equal to -1. So this is satisfying. Similarly x2. So x is equal to x2. What will happen? x2 minus x1. Here is x2 minus x1. The both will cancel, numerator and denominator, and 2 minus 1 is 1. So it will at node 2 zeta is equal to +1. So this will satisfies. So polynomial equation. For deriving its shape function, first we will choose the polynomial equation. It is a two-noded element. U is equal to a0 plus a1 and zeta. This is equation 2, polynomial equation to derive its use to derive the shape functions of this two-noded bar element. So in this we know the boundary conditions. What are the boundary conditions? At node 1, zeta is equal to -1, u is equal to u1. Similarly at node 2 we know that zeta is equal to 1 and u is equal to u2. These boundary conditions has to substitute. These two boundary conditions has to substitute in equation 2. So we will get, after applying the boundary conditions, we will get this equation. u1 is equal to a0 minus a1, u2 is equal to a0 plus 1 a1. So these equations by solving these two equations and two unknowns a0 and a1, you will get this values. a0 is equal to u1 plus e2 by 2 and a1 is equal to u2 minus e1 by 2. By substituting this constant values a0 and a1 in equation 1, in the previous slide we say u is equal to a0 plus a1 zeta is substituted in this equation. This is a0 and this is a1. So we will get the, and just rearrange the equations u1 and u2 and separate it, then we will get the 1 minus zeta by 2 u1 plus 1 plus zeta by 2 u2. So we can write this equation. U is equal to n1 u1 plus n2 u2. Here is n1 n2 are the shape functions of this bar two-noded element. So here n1 1 minus zeta by 2, n2 1 plus zeta by 2. These are the shape functions of these two-noded elements. These shape functions is used to find out the solution of this two-noded bar elements. So we know the relationship between the strain and stresses from the basics of mechanics of solids. We know strain is equal to dou u by dou x, change in length by original length. We can know that, and we have to use this chain rule of the differentiation because u is with reference to zeta. So strain is equal to dou u by dou zeta by dou x. So We know this u equation, just now we derived u is equal to this equation. So 1 minus zeta by 2 u1 plus 1 plus zeta by 2 u2. So in this equation first we have to derive with respect to zeta, dou u by dou zeta. So dou u by dou zeta is equal to minus u1 plus u2 by 2. Similarly, zeta is equal to, we know that the relationship between the natural and global coordinates. In this equation, what we have to do is differentiate with respect to x. This one dou u by dou zeta by dou x is equal to 2 by x2 minus x1. If x2 minus x1, we can say that this one is L, length of the element, because x2 minus x1 is initial to final value. We can say, in other words, this is the length of the element. So strain is equal to, substitute this value dou u by dou zeta and dou, here we have to substitute these values, we'll get this equation. Finally, strain is equal to 1 by L minus 1 u1 u2. This is the final equation. Strain is equal to beta B matrix into U. Here this B, what we say, that the relationship between the strain displacement matrix. So it is important to find out the stiffness matrices and stresses of this particular element. Strain energy. We know the concept of strain energy. In this strain energy concept, we can say that U is equal to half of its stress into strain into its volume. So this is the equation 1. This equation is shows the strain energy. So in terms of its stress and strain, because we know the stress is equal to E into B into strain. We know this equation in the previous classes we learned. So means we substitute this equation in the strain energy form. So this is the B transpose B U dx. Here is volume A by L and its material property. So after substituting this equations, finally we will multiply this equation and find out in matrix form, because we know the relation between the x and zeta coordinates. The zeta by dou x is equal to 2 by x2 minus x1. x2 minus x1 is, we can say that this one is the L, length of the element, also we can say that. So substitute it in this equation. Finally the relationship between this dx is equal to L by 2 dz. So we can rearrange this equation. U is equal to half of U transpose K into U. Here is this K, E, suffix E means it is the stiffness matrix of this two noded bar element. So the element stiffness matrix is equal to, you can say that this one AE by L and 2 integration with respect to d zeta minus 1 to 1 where it varies its magnitude. So multiplying this one, finally we will get the element stiffness matrix, this one AE by L into 1 minus 1 minus 1 1. This is the element stiffness matrix of this two noded bar element. Already we derived this element stiffness matrix by using its global coordinate system. For understanding purpose, we can also calculate this element stiffness matrix by using its natural coordinate system. So for understanding purpose, we consider work on problem. Evaluate the shape functions of this two noded bar element. Here has given the node 1 and node 2, its values x2 x1 values, and at the same time u1 u2 values also given. Find out the what is the displacement at point P. So we know the equations natural coordinate system, zeta is equal to this one, we know that. When find out the its zeta value, but substituting its values x1 and x2 values already we know that, and x value also we know that. Just substitute it and find out this. Zeta is equal to, final value is zeta at node 24 is equal to minus 0.5. So once we know the, then find out the shape functions. n1 shape function means 1 minus zeta by 2, 1 plus zeta by 2. We know this, substitute these values n1 and 2, we can find out the 0.25 and 0.75. At the same time, we may find out what is the displacement at point P, 24. So we know the equation U is equal to n1 and n1 u1 plus n2 u2. Substitute the values and find out its displacement. Value is 2. This is the displacement of this bar at a point 24.